Welcome, everybody, to this afternoon's press conference here at the 227th American Astronomical Society meeting in Kissimmee, Florida. I'm AAS Press Officer Rick Fienberg, and I'm very glad to see another nearly full house. We've been getting very good response to our briefings. Quick announcement. For those of you who attended the press dinner last night, if you haven't paid me yet, please try to pay me before you leave. If not, I know where you live. Everybody, please turn off your cell phones, or at least silence them. So if this is your first press conference at a AAS meeting, you may not know how we do it. I will introduce the speakers, and then they will present in order from right to left. Sometimes we do left to right, sometimes we do right to left. Today it's right to left. And then we'll do Q&A at the end. We always start here in the room, and then we go to the webcast. So I have two deputy press officers here with me today. Larry Marshall will be manning the mic here in the room, and Inga Heyer in the back is monitoring our webcast. If you're tuned in via the webcast, please use the text chat to let us know if there are any technical problems with the stream, and then during the Q&A, please use the text chat to let us know that you have a question. All right, so this afternoon's briefing features four new scientific results that are being presented here at the meeting. First, we're going to hear from Marco Ajello from Clemson University on the Fermi mission sharpening its high-energy vision. Then we're going to have two presentations on high redshift objects. First, from John O'Mara at St. Michael's College in Vermont, Fingerprints of the First Stars, the discovery of possible population 3 remnants at redshift 3.5. He'll be followed by Mark Broadwin from the University of Missouri in Kansas City. He's going to bring the redshift down a little bit to a little over 1.5, the most massive galaxy cluster at that redshift. And then we'll have Sukanya Chakrabarty from the Rochester Institute of Technology. Some of you may remember she's presented some results at briefings before, and she's got a very interesting follow-up result to present from the same line of research, using galaxy quakes to hunt for dark matter. So with that, I will turn it over to Marco, and we'll get started.
Thank you, Rick.
Sorry. Suddenly our cursor is not terribly responsive. There we go.
Hello, everybody. I'm presenting here some new results on the Fermi mission Sharpens its high-energy view. If you go to the next slide first, we are here introducing a new census of the gamma ray sky performed by the Large Area Telescope on board of Fermi between an energy of 50 gigaelectronvolts and 2 teraelectronvolts, which, for reference, is billions of times to trillions of times the energy of visible light. This is an extreme energy range which is typically available only to TV telescopes from the ground, and is now available also to the Fermi Large Area Telescope from space. And this is so because of the reanalysis of the entire photon data set collected by the Large Area Telescope, and this reanalysis is called PAS8. And this made the LAT a lot more sensitive to high-energy photons, in general 2 photons, and also sharpened its view. So this means the LAT is able to produce sharper images of the gamma ray sky. This makes it for a much more sensitive instrument than what it used to be. The image here on the slide shows the entire sky observed above 50 GeV in galactic coordinates. So the red strip that you see at the center is the galactic plane. And this is done collecting 61,000 photons detected above 50 gigaelectronvolts by the Large Area Telescope in 80 months of data, so a little over 6 years. You can see that the image shows different morphologies and spatial variations on all scales. You can see the galactic plane, you can see the Fermi bubbles right above the galactic center. You can see many point-like sources and also 2 famous regions like the Cygnus regions and the Vela region. If you move to slide number 2, this is what we found in this new census, which is reported in the so-called 2FHL catalog. Because of the improved sensitivity, the LAT has detected over 360 sources, which is an extreme large number of sources for this extreme energy range. For comparison, this is more than the sources detected by the predecessor of LAT, EGRET, in its final catalog after 9 years of data in its lower energy band, so above 100 MeV. Because the LAT as an improved vision, the LAT has also become more sensitive to spatially extended sources, so sources that occupy a large region of the sky, which is not just point-like. And the 2FHL catalog reports 25 extended sources, and it allows to measure the energy of all sources up to 2 TeV. Because of the sharper vision, each single source is localized much better than before, up to 15% better than before. Roughly 360 sources were detected, and vast majority is blazars, so supermassive black holes at the center of galaxies that are able basically to accelerate particles to near the speed of light and emit gamma rays. It's rather surprising the fact that in this high energy band, they are detected up to redshift of 2, which corresponds to roughly 10 billion years ago, 3.3 billion years from the Big Bang. 11% of the sources have a galactic origin, and 14% are still unknown. So this means there is still some space for discovery of new populations. I told that this was an energy range typically accessible to ground-based Cherenkov telescope, but because ground-based Cherenkov telescope have a small field of view, typically 5 degrees or so, and low duty cycle, they can only observe a certain number of hours during the year, while the LAT, on the other hand, observes the entire sky every 3 hours. 280 out of these 360 sources have not yet been detected by TV telescopes. So this means there is a large reservoir of target for Cherenkov telescope. If you move to slide number 3, this image shows a close-up view of the inner galaxy centered around the galactic center, plus or minus 30 degrees roughly on either side, and shows that there is a lot of morphology in the inner galaxy. It also shows that there are many sources that are detected. Roughly, the LAT has detected 100 sources in this energy band. 40 or 42 of them do not belong to our galaxy. They are just spatial coincidence. They are extragalactic objects. But 39, possibly more, are galactic objects, so they belong to our galaxy. Typically, galactic objects are associated to pulsar wind nebulae and supernova remnants. A pulsar wind nebula is the region of space around a pulsar, which is a quickly spinning magnetized neutron star that's launching a wind of electrons and positrons that's interacting with the surrounding interstellar medium and producing gamma rays. Similarly, a supernova remnant is the remnant of a massive star that, when supernovas exploded and produced a blast wave, which is sweeping through the interstellar medium and producing gamma rays. So it's clear two things. First of all these kinds of objects are at the end of the stellar evolution cycle, and the second one is that you would expect some spatial extension because there is something moving away from a central source. And indeed, as I'll show in the next slide, most of these sources are spatially extended. The interesting thing in this band is that all the galactic objects emit most of their energy above 1 TeV, while the extragalactic objects, they emit their energy at lower energies, so roughly 100 GeV. So it's easy, or it's possible, to recognize a galactic objects from an extragalactic object. And we believe, on the basis of their energetics, that half of the unidentified objects that lie in the plane of the galaxy actually belong to our galaxy. So if you move to slide number 4, the improved capability of Fermi allowed to detect and characterize extended sources, or sources that subtend some spatial area on the sky. This is a key important parameter if you can detect it and characterize it, because it tells about where the emission region can be. If there is a change of the morphology with energy, it tells about the propagation of particles near the source, and in general it gives information about the total energetic and the processes in the source. And in this catalog, there is a grand total of 25 extended sources which have been detected, and 5 of them are completely brand new. They belong, 3 of them to the pulsar wind nebula class, and 2 of them to the supernova remnant class. The very interesting thing of the LAT is that the LAT is sensitive to emission from small scales to very large scales. This is a little different than Cherenkov telescopes that are only sensitive to the emission of sources which are typically smaller than their field of view. And this is one of example. This is a new source reported here in the lower left, detected by the LAT, which is 2FHL J0431. It's a source which extends over 3 degrees on the sky, and this is comparable to the field of view of Cherenkov telescope. And the LAT detects it's fairly bright, and it's found to be compatible, especially compatible with a new supernova remnant detected in 2014. And most of the energy is emitted actually above 1 or 2 TeVs. So it's a very interesting object. Slide number 5 concludes basically the results, is the fact that the LAT has basically performed a brand new census of the high energy sky between 50 GeV and 2 TeV. This is a new energy band. It's typically was not accessible from space. It was mostly accessible from the ground, and because of the new capabilities of the LAT delivered with PAS-8, this energy band can now be explored very sensitively by the LAT. What the LAT found is a slew of sources, 360 sources, which is a very large number. Some of them may be very interesting. It discovered many spatially extended sources, which is very interesting to understand the physics of this object, and allowed us to measure the energetic of these sources up to 2 TeV, which is outstanding. It's being done from space. And they conclude here showing again the beautiful image of the entire sky seen by the LAT in 80 months of data. Thank you.
All right. Well, thank you, everybody, certainly very much for coming out here today. I'm John O'Mara from St. Michael's College in the great state of Vermont. And I want to talk to you today about some exciting new results that we've made looking for the fingerprints of the very first stars in the universe. And what's shown here is a lovely simulation courtesy of Britton Smith out in Edinburgh that details what we're really trying to do with observations. This is actually a computer simulation of the explosion of a star very, very early in the universe. And the reason why we care about these things is intricately related with the air you're breathing right now. You know, the history of getting to here means the history of having heavy elements, and early on in the universe, we didn't have those heavy elements at all, and so we want to figure out how they got, where they got, and when. First, I just want to introduce the team. That's myself at St. Michael's College, Neil Crichton and Michael Murphy. Neil was the lead author on the paper where the results are coming from today. And this work is coming out. It'll be online in monthly notice of the Royal Astronomical Society. And if you'd like a link to the preprint, it's shown here below. So let's take a quick heavy element history of the universe, right? To the best of our knowledge, the universe began 13.8-ish billion years ago, the Big Bang, and shortly thereafter, in the first 3 minutes, was Big Bang nucleosynthesis, the creation of the first light nuclei, hydrogen, helium, their isotopes, and a smattering of lithium and beryllium. But those were the first elements out there in the universe, at least in their nuclei. The electrons hadn't captured on yet. We had to wait 300,000 years for that to happen. The formation of the first atoms when the electrons first captured onto hydrogen, and this was the creation of what we now see as the cosmic microwave background, which has been such a wonderful tool for cosmology. So this is the entering of the universe into the atomic era, but not the era of stars and galaxies yet, right? The universe is too young, too hot. Let's fast forward quite a bit of time. Now, t equals 4 billion years after the Bang, and this is when the universe is forming stars and galaxies at gangbusters. This is the peak of cosmic star formation, when the galaxies are really turning on, dumping huge amounts of heavy elements out into their surroundings, taking them in, recycling, more generations of stars, more heavy elements in the universe, until we get to some point 13.8 billion years after the Bang, which is today, here talking in this room. This is sort of a history of atoms in the universe. If we cast this in stellar terms, we like to refer to things like populations of stars. Population 1 stars like the sun or the more new, more recent stars, they're the ones that have a lot of heavy elements in them relative to the early times. Going back in time and out into the halo of the galaxies and the globular clusters are the population 2 stars. They don't have nearly as many heavy elements, but it's clear that the history of the universe is very much the history of the increase in the relative amount of heavy elements over time. So we start off with nothing, and now we have a lot of heavy elements today. But it's obvious that I've left something out, and what I've left something out is the very first stars in the universe. We call these things population 3 stars, and according to various cosmological models and whatnot, those first emerged about 400 million years after the Bang, right? Incorporated into the first galaxies. But what we would really like to do is see the effects of those stars. They seeded the universe with the first heavy elements, and those heavy elements, those first heavy elements, beyond hydrogen and helium, were critical for the formation of all the stars after it. You needed those heavy elements to cool the gas to be able to form the stars. So it would be very nice if we could see the imprints of these things. But it turns out that this is observationally a very difficult problem. We're building the James Webb Space Telescope in part to find these things. And so it would be very nice if we could get at least a teaser trailer of what we might find with Webb today. And that's what I want to show. So first I have to show off the technique. I'm a lowly spectroscopist, so I don't have any fun pictures to show you, just a bunch of squiggly lines. So I'm going to give you my cartoon universe, and then I'll show a little bit of data, but it's a bunch of lines, who cares, right? My technique is the technique of quasar absorption line spectroscopy. So here in cartoon form, if we take a very bright, very distant object like a quasar, if it's at redshift 3.5, which is the redshifts we're playing in here today, that's when the universe was around 2 billion years old. And redshift 3.5 is 1.8 billion years. The light travels through the universe to us, in this case to the Very Large Telescope facility run by ESO in Chile, which is one of the telescopes that took the data. And due to the expansion of the universe, the light is cosmologically redshifted. But it doesn't just fly straight to the telescope. It passes through giant clouds of gas along the way over the large appreciable volume of the universe. And as it goes through these gas clouds, it gets absorbed, and we can see the absorption signatures, the fingerprints of the atoms in the gas, because we know how atoms work. We know atomic physics. And because we know atomic physics and we know how the universe expands, we can actually use these tools to figure out where gas is in the universe, how much gas is in the universe, and what's in it. And so what would be a smooth quasar spectrum actually looks like this garbage, right? It's packed with absorption. And as you go higher and higher in redshift, earlier times in the universe, we see more and more and more absorption. And you can see in this figure, which shows the amount of light as a function of wavelength, that in this case, there's a characteristic drop to 0 on the left-hand side of that graph. This is the signature of a pocket of gas that has enough gas in it that it absorbs all of the ultraviolet light from the background quasar. We call these things Lyman limit systems, just because the Lyman series of hydrogen, it's entirely eaten up by gas. And Lyman limit systems are the primary tool I use to figure out where gas is in the universe. And it's important for this question because there's enough gas in that Lyman limit system where we could detect heavy elements, even very trace amounts. In Lyman limit systems, historically, we've been looking at them for decades now, we find that there tends to be a floor. We've never really found a Lyman limit system with a measurable amount of heavy elements below about 1 part in 1,000 relative to the sun. But the realm of population 3 is below that. We need to go lower in heavy element amounts than 1/1000th of the sun. Fortunately, we have found just such a cloud. The gas cloud is found towards a quasar with a lovely name of J124957 minus 015938. There will be a quiz after. And what's shown here in the figures is just to show that I really did take some data and work with it. In the upper left is the model of the hydrogen in the gas. We see copious amounts of the hydrogen. That's what's causing the Lyman limit system. But more important for this is what's on the right-hand panel, which is the observed absorption. We detect absorption from heavy elements in various ionization states. So carbon, silicon are the primary tools we use in this. And there's 2 important things about it. We can measure it, but there's not much of it. It turns out that the heavy element amount in this gas cloud is at about 1 part in 2,500 relative to the solar amount. It is the lowest metallicity or the lowest amount of heavy elements ever determined in a gas cloud like this when you can measure those heavy elements.